Yesterday we talked about the addition rule. If we go over the addition rule, if I wanted to find A or B, it would be A plus B, and then I would have to subtract out the common A and B, correct? And then we also talked about what happens if they are mutually exclusive, right? If these two are mutually exclusive, that means that A and B cannot happen. They can't happen at the same time. Therefore, this guy is 0, it goes away, and this winds up being if they are mutually exclusive. Okay? All right? So that's how far we got yesterday. Today we're going to talk about the multiplication rule. And if you look at the multiplication rule, the bottom of page 150, bottom of page 150 shows you the P, A, and B is P of A times P of B, given A has already occurred. Okay, this is how you read this. This is a conditional probability. It is the probability that B will occur given that A has already occurred. Okay? All right? So this is the multiplication rule. Okay? This is the multiplication rule. Multiplication rule. To find the probability that event A occurs in one trial and event B occurs in another trial, multiply the probability of event A by the probability of event B. But be sure that the probability of B is found by assuming that A has already occurred. Assuming that A has already occurred, right? It's conditioned on that. Okay, A has already occurred. All right? So one of the big things that the book talks about is, okay, now I told you that you're always going to get, you're going to get mutually exclusive and independent confused. And we kind of briefly talked about it. Okay. Independent means that it doesn't matter what's going to happen, right? It doesn't matter that Evan is wearing red, given that Spencer is wearing blue. Okay? They can happen at the same time, so they're not mutually exclusive, right? As of right now, right? You're wearing red, he's wearing blue. Okay? But the probability of him wearing blue is independent of whether or not Evan's wearing red. You see that? Right? In other words, the probability of Evan wearing red, okay, is the same as if, so given that Spencer is wearing blue, the probability of you wearing red is the same as just you wearing red. Does that make sense? Also, another thing that I can say here is that the probability that Spencer is not, given that he's not wearing blue, the probability of you wearing red is the same as just you wearing red. Okay? They're independent of each other. Does that make sense? I mean, it has no bearing whatsoever on what's happening there. Okay? So, it would be like we're flipping a coin, okay, and we're calculating the amount of heads, right? And I am flipping the coin, and I flip no less than 10 heads in a row. So I get head, 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 I'm going head. So what's the probability I'm going to hit a head the next time?
50-50.
The same thing. They're independent of each other, right? It doesn't matter what happened before. You see that? Okay. So, now let's go ahead and think of this within the realm of with replacement and without replacement. Okay, you guys had to do this in the homework, right? You talked about with replacement and without replacement. Okay, so let's say that I have a bag and I have 8 reds, 7 whites, marbles. What's the probability of me picking a red marble? 8 out of 15, right? Because there are 15 marbles, 8 of them are red. So it's 8 out of 15, right? Okay. Then, so I picked a red, and I picked the next one without replacement, without replacing that red back in. Now how many marbles do I have altogether? 14. So the probability of me picking a red is what? 7 over 14. Can you see that now this guy is not independent of this guy? Right? This guy is directly dependent upon what happened here. Right? Whether I picked a red or white shifts the probability altogether. However, if I pulled the red one and then I put it back in, now I'm doing the next one with the replacement because I'm replacing the one back in. What's the probability then? Still out of 8, 15. 8 out of 15, right? Do you see the difference there between probability of picking with the replacement and without replacement? Where picking without replacement would be a dependent thing, whereas when I pick with replacement, when I replace it back, then it's independent, because it really doesn't matter. It's just like 10 heads in a row, the next one, still 50-50, right? Okay? Right? So that's the difference between independent and dependent within the picking with replacement and without replacement. Okay? All right. So that should be pretty good. Let's go ahead and go to example 4, page 151. Page 151, example number 4. Now you're going to go ahead and read that for us, please.
Example number 4. Lists only the 50 test results for the subjects who used drugs from table 4-1 as shown below. Positive test results 45, negative test results 5, total 50.
A, go ahead.
If 2 of these 50 subjects who used drugs are randomly selected with replacement, find the probability that the first selected person had a positive test result and the second selected person had a negative test result.
Okay, so we're doing with replacement. With replacement, meaning that these two things are dependent or independent? Independent, right? Because we're replacing it back in, right? Okay, so the first we're going to do what? We're going to pick a person with a positive test first, right? So what's the probability of that happening? 45 out of 50, correct? And then they want to pick one that is negative test result, so it would be what? 5 out of 50, correct? Okay, this is how you run it, right? B, repeat part A by assuming that the 2 subjects are selected without replacement. So if it's without replacement, the first one's going to be the same, correct? Right, first one's going to be the same. What about the second one? 5 out of 49. Correct? Okay, all right. So that's the difference there. Flip the page. Okay. Sampling. Now we're going to talk about sampling. Okay? Sampling. In the wonderful world of the sampling methods are critically important. The following relationship holds. Sampling with replacement. Okay, if you sample with replacement, in other words, you sample one, put it back, and you put it again. Those are independent, correct? The sampling without replacement would be considered, or would be dependent, right? Because it depends on what happened on the first trial, right? The second one has a direct effect on that, okay? Now, there's an exception there. It says treating dependent events as independent. So sometimes when we are sampling without replacement, we can actually say, yeah, we're sampling without replacement, but guess what? We're going to just say it's the same as if we sampled with replacement. Okay. And so an example of that would be that, let's say that I have 100,000 batteries. I have 100,000 batteries, of which I know that 5 of them are bad. Okay, and I want to pick 3 of them. I want to find out what's the probability of me picking all 3 that are good. Okay? So how many good batteries are there? One more? Is that correct? No, that's too many. That many 9s, right? So this is how many good ones I have. This is how many bad ones I have, right? So I'm going to pick. So if I'm going to pick with replacement, it would be what? 99995 over times 99995, because I'm replacing it back, right? All right, times 99995. Okay, this is with replacement. Without replacement would be what? The same. The first one would be the same. So this is without replacement. The next one would be what? 9999. How many good ones do I have now? I've already picked one, right? So there's one less. And there's now one less battery. Correct? The next one would be 99993. 99998. Get your calculators out. Calculate this one and calculate that one.
I think the free Texas Roadhouse went out.
We should get your 9s straight here. What do we get here? Anybody? 0.99985. Everybody else get that? You get that one? Everybody got that? We have an imaginary calculator there, Isaac.
I'm just writing down.
9.99.
What is this one over here?
0.99985.
Oh,
But one of them is 0006. That one's 0006.
this one's 006 and this one is just
0075.
007. Oh my goodness. Can you see how these would be virtually the same number?
Yeah.
Right? Can you see that if I'm sampling with replacement versus without replacement is actually the same? Right? Because I'm sampling such a small quantity, right? I'm sampling 0.005%. When I'm only sampling 5 out of 100,000. Okay? So, that's why if you look in the green box on page 152, what does it say? Read that for me, Daniel.
What?
Huh? What?
Where? When
152.
sampling without replacement,
Uh-huh.
and a sample size is no more than 5% of the size population, treat the selection as being independent, even though they're actually dependent.
Okay, so when you are sampling less than 5%, okay, which this is definitely less than 5%, I can safely assume that sampling without replacement is just about the same as sampling with replacement. Okay? And this is a very important part because this gets tied into later on with when we do the normal distribution. Okay? So make sure you understand that. If you are sampling less than 5%, I can treat this as if they were independent draws, even though they are dependent events. Okay? All right? Okay, so that's example number 5 is basically the same thing we just did on the board with much easier numbers to deal with. So we kind of short-circuited that one. I'll let you do the birthday part, and we are done for the day. Okay. So in conclusion, what did we talk about? We talked about in the multiplication. We talked that the multiplication rule was what? The multiplication rule was P of A is equal to P of A. I'm sorry, A B is the same as PB given A. Okay? All right? This is the formula. Okay, now we talked about independent versus dependent, which is totally different than mutually exclusive. Okay? All right? We all remember this? All right? Okay, we're good.